This video derives the well-known Gordon growth valuation formula for equity using the concept of stochastic discount factor and physical pricing. Now, the example that we consider is a firm whose dividend shocks are all non-diversifiable for the representative investor. This says that all dividend shocks are systematic and hence compensated in equilibrium by a risk premium. So mathematically, we write the idea as follows. dd over d equals gdt plus sigma d times dbm. And dm over m equals minus rdt minus lambda dbm, where bm are Gaussian shocks to the stochastic discount factor and hence non-diversifiable shocks, which earn a risk premium lambda t dt. So now the way it's written here, dividends are driven by the same shocks than the SDF. That says all dividend shocks are systematic. Now we value the dividend stream dt with the SDF in combination with the empirical probability measure. Now let's do that. The price at time zero is defined to be the expectation as of time zero under the empirical probability measure of all future dividends discounted by M. Now D here is the cash flow, MT is the time t value of the SDF, and P highlights that we use the empirical probability density function when evaluating the expectation. Now, due to linearity, we can put the expectation into the integral, and therefore we get that the price is the integrated expected discounted value of future dividends. Now, in order to determine that expectation, it's easier to work with the differential representation. So we therefore apply Ito's lemma to derive d of m times d, which gives us the following expression. The last part, this instantaneous covariation between dividends and the SDF, that will be the notion of the risk premium. So let's divide that equation by m and by d, and we end up with the following representation. Now we plug in the Ito SDEs that we assumed at the beginning of the video, and we end up with the expression that dmd divided by md equals g dt plus sigma d dbm minus r dt minus lambda dbm minus sigma d times lambda times dt. Now solving for mt dt as a function of m0 d0 gives you the following expression here. Now just take the expectation as of time zero and you end up with the insight that the expected discounted value of a dividend payoff in t is simply today's dividend times the exponential of g minus r minus sigma d lambda times t. Yeah, so let's do some economics here. You see that the present value of these dividends, or the expected present value of a dividend, is the dividend in 0 times e to the g times t. That would be the expected growth rate of dividends. Now you discount by the risk-free rate, and you also discount by a risk premium, by sigma d times lambda. Okay, now let's go back to the pricing expression. Yeah, we said that the price is defined to be the expected present value of all future dividends. Now we swap again the integral with the expectation. We just solved what the expected present value of a dividend looks like. We plugged it into the integral. And now we define the exponent of g minus r minus sigma d lambda to be a constant c. Now we assume that c is smaller than 0, and now which implies that the integral is finite. It converges. And therefore we can solve that the price in 0 divided by the dividend in 0 is nothing else than minus 1 over c. Plugging in the c again, it gives us 1 divided by R plus sigma d lambda minus G. Now that is the well-known Gordon growth formula, which says that the price-dividend ratio for a firm that pays dividends up to infinity with a constant growth rate G and a constant discount rate that consists of the risk-free rate and the risk premium just coincides with exactly what we have here, with 1 divided by the discount rate minus the growth rate, where the discount rate has these two components, risk-free rate and risk premium.